In the world of AI, there's an idea that, honestly, sounds a little bit like science fiction. It's a concept that could completely flip how we build intelligent machines. Today, we're going on a hunt for the AI lottery ticket.
So, for years now, the rule in AI has been pretty straightforward. If you want more power, you build a bigger model. And it's worked. We have these absolutely colossal neural networks now that can do things we thought were decades away.
But there's a huge catch, a really big one. Training these monsters costs a fortune. We're talking massive amounts of time, money, and electricity. It's become a huge bottleneck, really, a game that only a few tech giants can even afford to play.
Which, of course, leads to the most obvious question in the world. If the end goal is to have a smaller, more efficient model, why don't we just build a smaller, more efficient model? Why go through all the trouble of building a giant one first?
And this is where things get really weird. It's a puzzle that stumped researchers for years. So on the one hand, you can take a huge, trained network and just start snipping away connections. You can prune it by like 90%, and it still works great. But if you take that exact same small, efficient structure and try to train it from the very beginning, it's a dud. It just fails. It doesn't learn properly. How does that make any sense?
Then, back in 2018, a couple of researchers, Frankel and Carbon, dropped this paper with a pretty wild idea. They said, look, what if these giant networks have these little hidden gems inside, tiny subnetworks that they called winning tickets? And the key, they said, is that these tickets were special from the moment they were created. But why?
And that idea is called the lottery ticket hypothesis. The theory goes like this. Think of a giant, brand new, random AI network, not as one single machine, but as a massive bin full of lottery tickets. Most of them are duds, completely useless. But buried in there are a few winning tickets, these little subnetworks that, just by sheer random luck, got the perfect combination of starting settings. They were basically born to win.
Okay, it's a fascinating idea for sure, but it's just a theory, right? How in the world could you actually prove it? How would you dig through millions, or even billions of connections to find one of these so-called winning tickets and show that it was lucky from the start?
Well, their experiment was just brilliant. So first, they do the normal thing, train a big network. Then, step 2, they prune it. They get rid of all the weakest connections. Step 3, they've got the leftover structure, right? The skeleton of what might be a winning ticket. But here's the genius part, the big twist in step 4. They take that skeleton and they rewind its weights, resetting them all the way back to the original random values they had at the very, very beginning, before any training happened. This last step is the key to everything.
Because that setup created the ultimate showdown. What really matters for success? Is it just having the right structure? Or is it having that structure with its original lucky starting numbers? To figure it out, they put them head to head.
So on one side, we have the real deal, the winning ticket. That's the pruned structure, but with its original lucky starting values restored. On the other side, we have the exact same structure, but they threw out those original values and just gave it a totally new random set of numbers. Remember, the architecture is identical. The only difference is that starting point. And the results were just astonishing. The very first thing they noticed was a crazy difference in speed. The real winning tickets learned so much faster.
Just look at the data here. It's pretty wild. The big, original network took about 15,000 rounds to train. The winning ticket, which is just a fraction of the size, got there in only 9,000 rounds. That's almost 40% faster. And now look at the other ticket, the one with fresh random numbers. Same small size, but it was actually slower than the original giant network.
But here's where my jaw just dropped. It wasn't just about speed. These tiny winning tickets, they actually ended up being more accurate than the gigantic network they were carved out of. And the numbers here just seal the deal. You've got a winning ticket that's less than 14% of the original size, and yet it scores a higher accuracy. A tiny network beat its massive parent. And again, look at the re-initialized one. Its accuracy went down. This was the smoking gun. It's not just the structure that matters. It's the structure plus that lucky start.
The authors really said it best themselves. They wrote that the original initialization withstands and benefits from pruning, while the random one's performance immediately suffers. In other words, that lucky draw at the beginning is everything.
So you might be thinking, okay, that's a cool trick, but this is so much more than that. This discovery really forces us to rethink what's actually happening when an AI learns.
So why does this all matter? Well, for one, imagine if we could find these tickets before training. We could build models way faster and cheaper. It could also inspire completely new ways to design AI from the ground up. And, maybe most importantly, it could finally explain the mystery of why these huge bloated networks are so darn good at learning in the first place.
And that brings us to an even bigger, more profound idea they proposed: the lottery ticket conjecture. What if the learning algorithm, the thing that trains the model, isn't actually teaching the whole network? What if its real job is just to find the winning ticket that was already there, hiding inside, and then pour all its effort into training just that one tiny, perfect part?
Which leaves us with a pretty mind-bending final question. Are we spending billions of dollars building these absolutely enormous AI models, not because we need all that size, but because they are basically just really, really expensive lottery machines, designed to find the one perfect, tiny, and incredibly lucky network hidden deep inside?